All right, here we go. Day number 2 of topic 13. We're going to be talking about dilations. So what we're going to talk about today is I can select, apply, and adapt a variety of mathematical strategies related to similarities. So go ahead, pause this video as you guys are copying this down, and then come on back. So we're going to talk about triangles and dilations. So what we're going to do is we're going to start at this point J. And if I made lines through everything, all these dots, right, you would see that they all line up. Okay, so we're going to talk about the dilations about point J. It is easiest to see it online, so here it is online. Boom. Come on. There it is. So you're going to see there's my point J, there's my lines that come through, and I get the other triangle. What I can do is I can move this slider, and as you can see, the closer I am to 0, nothing happens because it's 0. And when I'm between the numbers 0 and 1, it gets smaller, which makes sense, right? If I was at a half, which is right here, it is half the size. If I'm at 1, it is the same size. And as I keep going up, if I go to 2, it is twice its size, and you guys kind of get the idea. And we can show the angle measures and the sides. So as you look at the sides, right, the ratio changes based on the scale factor. So if my scale factor is 1, my sides have a ratio of 1. If my scale factor is 2, my sides have a ratio of 2. But what do you guys notice? Nothing happens to my angles. The angles stay the same size. Nothing changes. So now we can answer some questions based on what we've seen. So as the scale factor changes, what do you notice about the measure of the corresponding angles? The corresponding angles have equal measure. Right? AKA they're congruent. Nothing changes. Number 9. What do you notice about the ratios of the lengths of the corresponding sides? The ratios of the lengths of the, I'm going to cut COR dot, I'm going to abbreviate corresponding sides remains the same, right? And that's talking about these numbers, right? All of them are 1.97, no matter what we do, right? If we want it as 1, then all of them are 1. If we want it as 2, then all of them are 2. So they all stay the same. Number 10, how is the ratio of the lengths of the corresponding sides related to the scale factor? The ratio is equal to the scale factor. Okay? The only time it's not is when the scale factor is 0, right? Because then nothing happens. So the ratio is equal to the scale factor, right? When it's greater than or equal to 0. We'll talk about the negative numbers later on. We're just going to focus on the positive numbers right now. So number 11. When the scale factor approaches 0, at what point does the image of the triangle become a reduction? Okay? Instead of an enlargement. A reduction, right? This word means it gets smaller. An enlargement means it gets, right, bigger. So if we go back to our pictures, which is here, at what point does the picture, so if this is at 1, right, everything is good. All of this is an enlargement. It's getting bigger. So the number 1 makes it the same, and then anything less than 1, but bigger than 0, right, makes our shape smaller, or aka a reduction. So in our notes, we can put down when the SF, otherwise known as scale factor, is between 0 and 1. Right, and if you want to be more specific, that means that triangle RST, right, our new triangle, is a reduction of triangle RST. Awesome. Okay, so what we're going to do now, we're going to practice more of this with the scale factor, and we're going to see what happens. Okay, so for number 12, this part here, here's my two triangles. Okay, and if you connected the R's, you can see they're at the same line. You can see the S's are on the same line, and you can see the T's are on the same line. So what happens when the scale factor is negative? So right up here, it tells me a scale factor of negative 1.4. So in my graph here, right, I'm starting here at 1, and if I keep going backwards and I get to negative 1.4, which is right there, that's what my picture looks like, which is the same thing in our notes. If you notice, right, as I come down, it's getting smaller, 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 smaller. I'm at 0. Now what happens? The T flips to the left side, the R goes from the bottom to the top, and the S goes from the top to the bottom, right? So everything kind of flips, otherwise known as reflection, right? Do you guys remember talking about reflections or rotation about the point J? So in our notes, what happens when the scale factor is negative? The image is on the opposite side of the center of dilation Well, why did I spell like that? I forgot a letter. Dilation. Okay, so what it means is this is my center, right? This image went from this side to the other side of my center of dilation. And what else happens? The image is rotated 180 degrees around. Right? So it gets rotated 180 degrees around and then is dilated. Sorry for all the writing, guys. Lots of writing today. So we take our image, it gets rotated around. I'm going to try and do this for you guys so you guys can see. Okay, so if we copy this triangle here, erase this, I'm going to erase all this. So there's my triangle. If I take my triangle, it's going to get rotated about the side and it's going to get put over here. Okay, and then from here, it gets dilated and it becomes bigger as it moves out, and then it becomes the same size as that one. So that's what we're talking about, right? So I can shrink it down, it gets to this size, and then it gets rotated about the side, and it comes back. So that is what we are talking about. All right, number 13, some fill in the blanks. I would like you guys to pause this video, go ahead and try and fill in all these fill in the blanks. All right, hopefully you guys went through and you guys filled this out. So if a figure is dilated, the image and the pre-image are similar, right? It is not exactly the same because a dilation makes it either bigger or smaller, so it is similar. If point S is dilated to a point S prime with the center of dilation J, the ratio JS prime to JS is constant. That constant is called the scale factor. Of dilation. The corresponding sides of the preimage and image are proportional. And then the corresponding angles of the preimage and image are congruent. Awesome. Look at us go. Rocking it out. Okay. Number 14, as we continue on. So 14, complete the following statements that describe a dilation with a scale factor S. Again, like you guys to pause this video, try and put in stuff. It's going to be like enlargement, reduction, just trying to make you guys think. So if you'd like to pause this video, try it on your own, feel free. Otherwise, you can wait about 5 seconds and I'll go through it. All right, so if the absolute value of S is greater than 1, the dilation is an enlargement. And this goes back to the pictures that we were talking about before, right? Anything bigger than 1 makes it bigger. So like right here, where am I at? So here's 0, right? As I get to 1, all of a sudden I'm at 1. Anything bigger than 1, you can see how my triangle gets bigger. So anything bigger than 1, my triangle gets bigger. So the next part it says, if it's between 0 and 1, and here's my picture between 0 and 1, and you can see it is smaller, but we're not going to use the word smaller. We're going to use the word reduction. So if it's between this, the dilation is a reduction. If S is equal to 1, the image and the preimage are congruent, right? It's the same exact picture. Some of you a little bit specific, right? They're congruent to each other. Congruent figures can be thought of as having similar figures with a scale factor of, the scale factor is 1 or -1, depending which way you'd like to think about it. If S equals 0, the image is a point at the center of the I keep spelling dial wrong, dilation. Okay, so what does that mean? So if I go back to my picture, right, here it is. I'm at 1, and as I get closer and closer and closer to 0, you see how it gets smaller, 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 and as soon as I'm at 0, you see how it goes away? Because it just turns into a point because all the dots come together, right? So as I'm at 1, it gets smaller, 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 smaller. All of a sudden it's at 0, it's just a point. If S is negative, the image is, right? We're just going to put rotated 180 degrees around the center. And then it is dilated. Awesome. Okay, that's it. So let me show you guys what this picture looks like. So if I'm starting here at 1, right, I'm going to go jump to -1. You see how the picture is exactly the same, right? It's just rotated 180 degrees. Then I can dilate it bigger or I can dilate it smaller. You guys see how that works? So -1, now it's getting bigger. -1, now it's getting smaller. So that's what E means. Okay, a couple more, and then we're done for this section. So this illustration shows a dilation with a scale factor of -2. What is the ratio R prime J to Rj? The ratio is the absolute value of the scale factor, is the absolute value of the scale factor. So what it would be is our scale factor is equal to the absolute value of -2. Pretty simple. How do I know that? Because it says it right here, -2. Okay? So it goes from this image and it gets rotated. So let me talk about it real fast, right? So I'm going to take this. Where's my drawing? This image here gets taken, and since it's -2, it gets taken and it gets flipped around. Let me get it so it's close. So it gets put right here. And now I take the absolute value of -2, which is 2. So then it gets bigger by a number of 2, and that's how I get to that picture. So that is what it is talking about. Next, do the relationships you found in question 14 hold true even if the triangle is distorted? Yes. This is for all triangles, right? In each case, the absolute value, right, is always equal. So basically, I'm just kind of abbreviating everything. Yes, it works for every single one, okay? If we want to be more specific, and I'm just going to add this in here, the corresponding sides, okay, and angles are congruent. There we go. Corresponding side, that's right. The ratio, there we go, of the corresponding sides and the corresponding angles are congruent. There we go, the ratio. Perfect. Number 17, as we move on. Write the definition of similar polygons. What it means to be a similar polygon, it means that two polygons are similar if and only if all pairs of corresponding angles are congruent and all pairs of corresponding sides are proportional. Whew, that's a lot, right? So the two angles are similar if and only if all pairs of corresponding angles are congruent and all pairs of corresponding sides are proportional. And I'm going to show you what we mean by this, okay? And this is number 18. So for number 18, here's a polygon, two triangles, okay? So we're going to talk about the sides. 1 to 2, right? 3 to 6, and let's use purple, 2 to 4. These are all proportional because what's 1 times 2? 2. What's 3 times 2? 6. And what's 2 times 2? 4. So all my sides are proportional with the scale factor of 2. Then I have 3 lines over here for my angles, 3 lines for my angles, 2 lines for my angles, 2 lines for my angles, 1 line for my angle, 1 line for my angle. So all my sides are proportional and all my angles are congruent. So similar, these pairs of polygons are similar. We can say that A is similar. Let's go to B, okay? If we're looking at B, congruent, congruent, right? Congruent, congruent. And now we have single line, single line. These are double lines. So right away I can tell you, right, that this is not a similar polygon because my sides do not have a proportional, like the sides are not proportional. So 1, 1, and the one that makes it wrong are these two. If these two both had this symbol, then yes, it would be congruent, but it doesn't have that, right? And all of our angles are congruent. They're all 90 degrees. So the part that makes it wrong is the sides. Let's talk about C. Well, right away, we can tell you that it's not similar because this has how many sides? 4. This has how many sides? 5. So there's no way that that can be similar. And now we have D, which is basically the same thing as B, right? 1, 1, 1, 1, 2, 2, 2, 2. So we just multiplied everything by 2, right? And all of our angles are the same. So D is similar. And boom, just like that, we're done. Go ahead, go through the rest of this for the rest of your remaining time. Go through 19, 20, 21, 22, 23,